let's go ahead and talk about what we're going to try to put the mic on first. What we're going to be doing today, we're starting a new unit. It is on solutions. I didn't have it up there. The assignments, notes, and objectives are all here, but they're in your yellow packet. We're going to learn today what a solution is. We're going to do a fed activity. We're going to do a little lab on solutions, suspensions, and colloid. So we've got a lot of activity stuff to do today. The assignment, 8.1 is your daily work that's in the packet kind of stuff. So you'll just turn that in there. And then you had your quiz. Next time we'll learn more about molarity. So that's what's going on right now. Let's go ahead and get started. Solutions and mixtures. Again, today the objective is to be able to label the parts of the key curve in a phase diagram and to be able to read them. To describe the solution in terms of solid and solvent, and to determine whether mixtures are solution, suspension, or a colloid, and that's where our lab comes into play. So you'll get to play with them a little bit. This is what's known as a phase diagram. You need to be able to identify each part of this. So I've given you a phase diagram that you can write this stuff on. So it's taking everything that we've learned with phases, like solid, liquid, and gas, and putting it on a Y graph. So the line there between solid and liquid is what we know as melting or freezing. That is a line that is affected by pressure. So as we have pressure increasing, you see that line sort of fading towards a higher temperature. The line between liquid and gas also is affected by pressure and temperature. So if the pressure is high, the temperature is going to be high in order to go from vaporization to condensation. The point below what we call a triple point is a point where I have gas, liquid, and solid. They all coexist. In other words, I can boil ice water. Below that is what is known as a place going from a solid to a gas or a gas to a solid. This is where we make dry ice by forcing it under a lot of pressure and a very cold temperature. This is where sublimation occurs, where dry ice turns right into gas and doesn't go through the liquid phase. Then we have out here what's called a critical point. At that point, it doesn't matter how much pressure I put on it. The temperature is so high, the gases have so much energy, there's no way I can get them to go back into a liquid. So past that point, past that temperature and that pressure, it doesn't matter what I do, I have gas. So I'm going to give you a second to write all that down because that's a lot. You need to be able to tell me what's happening at any point in time on that. Okay? So I could give you a pressure and a temperature, and you would have to come to the temperature, come to the pressure, and say, oh, it's right here, it's a liquid. So this would be something like they would do on the ACT, having you read a graph, being able to interpret what the data is. Given a pressure and a temperature, I could also say going across at 1 atmosphere, I go from a solid. At this temperature, I am melting. At this temperature, I'm a liquid. At this temperature, I boil. And then beyond that, I'm a gas. Or I could be given a temperature and saying at this pressure, I'm a gas. When it turns to this pressure, I'm now a solid. And I go through deposition. So depending on what they give you, you should be able to determine what phase you're in or what would happen if I increase the temperature. Yes?
So what's a triple point again?
Triple points where you have solid, liquid, and gas all coexisting. So you can actually boil ice water. And I used to be able to do that, but our vacuum sort of got messed up, so it doesn't go down as well as it needs to. Sort of cool to look at, though. But how many of you here backpack at all? The backpackers and the backpacker? Okay, if you take, say, macaroni and cheese that you love down here, and you take it backpacking with you because it's lightweight, and you get up at the top of the mountains and you try and make macaroni and cheese, what you end up is mushroomy and cheese. It never gets hot enough to actually cook the noodles because the pressure's so low, the boiling point becomes much lower. And because it's much lower, it never does cook that macaroni. You end up with mushroomy. So that's why a lot of backpackers pack stuff that's already been cooked, like in MREs. all you have to do is heat them up, even though they're a little bit heavier. If you just have to rehydrate it, that's one thing, but if you have to cook it, that's another. So another thing they do is dehydrate the food. Okay, so here we have two things that we're adding to this graph. It's normal melting point and normal boiling point. All that means is I'm coming across that 1 atmosphere on that chart. And 1 atmosphere is what we call standard pressure. Standard pressure can be a bunch of different things. It could be 760 millimeters mercury, 760 torr, 101.3 kilopascals, but it's all 1 atmosphere. It's all equal to 1 atmosphere. So you just add that to your chart, knowing that wherever the pressure is 1 atmosphere going across, wherever it hits those two lines, going from solid to liquid is normal melting point, going from a liquid to a gas is normal boiling point. Now if it came across below here, then I would only have 1 normal point and it would be a sublimation point. All right, so we talked about triple point where it is solid, liquid, and gas. We've got a solid, liquid, and gas phase. Just remember the solid phase is closest to the y-axis and the gaseous phase closest to the x-axis. Liquid's always in between. We get our critical point. Below that pressure, we're still gaseous. Above that pressure, we actually get what's called a supercritical fluid. And that's where a lot of research is going on right now, is above that point. The problem is having that high enough pressure and high enough temperature to be useful in industry. Okay. All right, so here we have, it didn't cover them up very well. You should have another graph, or maybe not. Maybe I'm just giving you some to look at. Okay, so in this area, looking at this is pressure in bar. So 100 to 1.3 bar is standard pressure, but you don't need to know that. This is just an older chart. I just wanted to show you that you should be able to really quickly and easily label what they are, solid, liquid, and gas areas. That's about it that I wanted to make sure you knew, and coming across that this would be the melting point and freezing point, and this would be the boiling point. But you should be able to label the areas. Okay, so what is a solution? A solution consists of a solid and a liquid usually. Not always, but most often. The solid is what's being dissolved. That's called a solute. What is doing the dissolving is called a solvent. Putting it together gets a solution. Okay? So, when we talk about solids, think about that's the thing that's being dissolved. When we talk about a solution, it's the things together. And a solvent is what's doing the dissolving. The most universal solvent that we have is water because it has a polar, look, it has oxygen to a hydrogen to a hydrogen, and it has 2 unshared pairs of electrons on here. So this side right here is slightly negative, and this side down here is slightly positive. So anything that has a positive and negative side, water can dissolve. Okay. All right. Solid is, again, what is being dissolved, and solvent is what is doing the dissolving. Why are chemists so great at solving problems? They have all the solutions. Okay, if we're going to make tea and mix sugar in it, the sugar and the tea are solutes. The water is a solvent. So you can have more than one solute. And then, of course, sweet tea is a solution. There are things that look like solutions that aren't. So a true solution is anything less than 10 to the minus 7 centimeters in diameter. So very, very small. But there's this area in between what we call solutions and suspensions. It's called a colloid. And a colloid has a diameter between 10 to the minus 7 and 10 to the minus 5. Okay, so it's small enough to stay in solution, but it's big enough to catch light. And this is where we're able to say whether it's a true solution or if it's not. A suspension is like, you remember when you were little and you got sick and your mom went to the doctor and you got this stuff, it was either white or it was pink, and you had to keep it in the fridge, and mom had to shake it up every time she had to give you a dose of it. That's a suspension. That's usually amoxicillin or an augmentin suspension. A colloid stays in solution. You don't have to shake it up. But if you put light through it, the light scatters. So, another way that we can talk about solutions is concentrated versus dilute. Concentrated just means you have a lot of solute and a little bit of solvent, or a lot of solvent with a little bit of solute. So this is a dilute versus a concentrated. We also have heterogeneous versus homogeneous. We've used these words before. Homo means same throughout. Hetero means different. Okay? So as we're looking at something that is the same throughout, like salt water, that would be a solution. Chocolate milk, the chocolate milk will actually settle out if you let it sit there for a while, if it hasn't been homogenized. And that would be a suspension. Okay, so we need to know the difference between a solution, suspension, and a colloid. You guys are sitting there staring at me, and I wonder what's going on. Are we not having... Okay, so what we want to do is we want to add this on the back of the yellow. So this just gives you some ideas. So as you're looking at things, I want you to have some ideas. So sometimes I didn't really update this from last year, so we need to add a few things. Just give yourself some ideas so that you sort of know what's going on there. You don't have to put all of them down, but give some ideas. Okay, suspension, muddy water. If you go take a sample of river water and just let it sit after there's been a storm, you'll know it's settled out. Marbles in water, we already know that that's a suspension. That depends on the size of the marble. Sometimes it's not even a suspension, they just are already separated. Pebbles in water is probably better. Salmon water, like at the ocean. Get them to settle out. Colloid, ice cream soda, like a root beer float. Okay, got some ideas on each of them. You don't have to have them all down. Okay, so suspensions versus colloids. Suspensions and colloids are not solutions. So as we look here at around B, if you can't find us, suspensions are particles large enough they settle out, if not constantly stirred. So if I'm not sitting there stirring it, my chocolate milk, especially the chocolate milk my children make for me, made when they were little, they put a lot of chocolate in it. If you don't sit there and stir it while you're drinking it, you end up with a water spitting chocolate down the bottom. Okay, they settle out if not constantly stirred. Colloids, however, they will stay in solution. It'll look a little foggy. It'll look a little like it's not clear all the way through. Some of them actually will look like they're clear all the way through until you shine a light. But these are the ones that are in between the size of a suspension and the size of a true solution. You okay? Need a few seconds more? Okay. We're going to actually experience these today so you can actually see the difference between them. Okay, moving forward. You don't have to write these down. These are just some types of colloids. So as we look at them, these are some things that you can think of. Fog. How many have experienced driving in fog? Yeah, it's so much fun. Smoke, airborne germs, whipped cream, suds, milk, mayonnaise, paint, clays, gelatin, marshmallows, styrofoam, butter, cheese, ruby, glass. A lot of these you're going, butter, cheese, what? It's how it's dispersed within it. So if you have butter or cheese, they're not going to fall apart. They're a mixture of stuff. They have a special kind of colloid. We're going to be working more with liquid colloids than we are some of these, like the solid emulsion or the solid foams. We're going to be working with more of a solution kind of colloid. Okay, so when we have a colloid, we're going to shine a light source through it. If the light source just shows here and here, it's a solution. It just shows me where it goes in, it's just a solution. But if it actually comes in, I can see with a pathway or it lights up the whole solution, that's a colloid. A suspension will also show like a colloid. It'll light up, but then after a while, you'll find things settling out. It still might have some colloidal size particles above it in the solution and still show a pathway through, but some things will have fallen out. And that's how I can know it's a suspension and not a colloid. Okay? But a colloid will never have stuff fall out of it. So to tell the difference between a solution and a colloid, the only way I can do it is shine a light through it. Okay? That light scattering is called the Tyndall effect. So when I ask you if there's a Tyndall effect, that means is there that light shining through? The bottom one is very, very obvious. The top one is not as obvious, but you can still see it. Anytime you've driven in fog, you've seen the Tyndall effect. Anytime you see light coming through the clouds, you're seeing the Tyndall effect. Or walking in the forest and seeing the light coming through the trees, and you follow the pathway of that light, that is the Tyndall effect. Okay, so you've got a colloid of the air. Fog we're very familiar with, walking through it, and driving through it. So how does a solution form? A solution forms because that water molecule is slightly polar. Okay? And what happens is that it actually pulls it apart. And we're just going to go through it, so just basically get the idea. This right here is a representation of a salt crystal, and the salt crystal will go positive, negative, positive, negative, positive, negative. And it sort of rearranges itself into what we call an ionic crystal. Well, the water comes, and the negative end, the red end, will attach to a positive, and the positive end will attach to the negative part of that crystal, so it'll pull it apart. And it's called what we call solvate. No, it's not solvation, it's solvate. And it just surrounds each of the ions of crystal. It doesn't react with it. It doesn't make a new compound. It doesn't form a reaction. It solvates it. So if I dehydrate it, I get my crystal back. Okay? It hasn't changed the crystal. So just because something looks like it disappears, we've got to be careful, because if I take a metal and I put it in hydrochloric acid, it will disappear, but I've got a color change, okay, number one, and when I dehydrate it, I get something new. So if I dehydrate it, I get the same thing I had before. It's a solution and it's been solvated. If I dehydrate it, I get something new, a reaction's taking place. And I actually get something new. Okay? Dissolution is a physical change. A chemical reaction is a chemical change. So you've got to be able to know the difference. The big thing is, by evaporating, you can tell the difference. Okay? Your turn. I want you to talk to each other really quickly. I know this is hard because you're so far apart. But see if you can come up with a solution that is unique, that nobody else around you can think about. See if you can do it before anyone else can. Quick. And be sure you identify the solvent and solvent. I'm going to give you 1 minute. You've got to come up with something unique, something somebody else hasn't.
Water and sugar.
Okay, that's taken now. Somebody else got to figure something else.
Water and salt.
Water and salt. Okay, 2 easy ones. Faster, faster, you guys.
Water and Kool-Aid.
Water and Kool-Aid. Okay. All right. Uh-oh. Now it's getting harder. Coffee would work. Okay, got 2 of you more. See what else you can figure. Tea would work. Uh-oh. Now we're down to the hardest one. Okay, an idea? And we got an idea to help her? Hot chocolate, yeah. Okay, especially if you make it with water and powder, right? Okay, awesome. So, when we form a precipitate is a solid that comes out of solution. You have to combine some substances to get them to react, and then something falls out. So, we have a solution, we have suspension, and if that suspension falls out, we end up with a precipitate on the bottom and a supernate on top. So when I ask you to collect a supernate, I'm asking you to let it sit, collect what's on top off. Okay? So you need to just know those words. Precipitate, falls out, supernate is what's left on top. And that's that little thing on the right-hand side at the bottom of your thing, your notes there for this. So I put the names in there for you. Right-hand side of your notes, sorry. We okay to go forward? You got the names down? So precipitate, supernate, suspension, and then solution. You okay? Speak now or forever hold your peace. Okay, so most of us know soluble and insoluble. If it's soluble, it will dissolve. If it's insoluble, it won't dissolve. That's pretty easy. Soluble substance, salt dissolves in water. Insoluble, you all have heard this before, oil and water. Oil and water don't mix. That's because oil is nonpolar and water is polar. So you definitely see a difference. That's how they make the lava lamps. Okay, they just heat it up and get it moving. Okay. So soluble versus insoluble. Next one, though you probably have not heard of before. Oops. It's miscible and immiscible. The way I keep it straight is miscible sounds like mixable, and immiscible, anytime you put im in front of anything, I-am, it means not. Immobile, not mobile. Okay? So, miscible, mixable, immiscible, not mixable. There's some words that we need, vocabulary we need to know. All right, so miscible versus immiscible. Water and methylene, you can see a line here, that means they're not mixable. But acetone and water are mixable, there's no line. We can make our density columns. That would be immiscible. Water would be miscible. Okay? Able to mix, not able to mix. Very easy, very quick and forward. Okay, what do you do when you need to make a solution? Call them my Kool-Aid rolls. Okay? If you were like my kids when they were young, they loved Kool-Aid. We made tons and tons of Kool-Aid. I think we kept the Kool-Aid people in money for a long time. Okay? But I had to be careful watching them make it because my son would like to add 2 cups of sugar instead of the 1 that it was supposed to be. And then they wouldn't stir it. And so you get this really sour, nasty on the top and really sickeningly sweet sugar on the bottom, syrupy. So, Kool-Aid rolls. Number 1, we use regular granulated sugar. If we use powdered sugar, it would dissolve faster. If we use sugar cubes, it doesn't dissolve as fast. Number 2, you could heat it up to dissolve it better. So if you had to, you could heat it up. My mom used to give us a form of Pedialyte, which was Kool-Aid mixed with warm water, or Jell-O mixed with warm water when we were sick. Gives me bad mojo in my mouth, I'll still. Okay, so I can change the size of the particles I'm trying to dissolve. I can heat it up to dissolve it faster. And the other thing is, you've got to stir it, right? it's not going to come together unless you stir it. It'll take an awful long time. So those are my Kool-Aid rules. So basically when I'm making a solution, I'm going to make sure the particles that my solid that I'm trying to dissolve is crushed up. If it's crushed up, it's going to dissolve faster. Number two, I'm going to make sure my water is warm so the solution will dissolve quicker. Number three, I'm going to stir it. Okay? So we'll do a Kool-Aid type lab in a little bit. So I want you to look at these. I think they're on your paper, are they not?
Yeah.
Okay, what is my solid in number one?
Sugar.
Sugar, right. Sugar is my solid. That means, what's my solvent?
Water.
Good. Okay, would you check the others? See what you can do with those real fast. Decide which is what. You already did it. Don't know the last one. I don't have the fourth one up there, do I? Oh, the third one, sorry. Okay. So the next one should be fairly easy. Our solid is NaCl. Our water is our solvent. But if you get to the next one, it says, okay, I've got 18 liters of nitrogen and 12 liters of oxygen. The solvent is always going to be your bigger thing. Okay, so here, my solvent is the 19, and my solute is the oxygen. Okay? All right. Okay, so we're going to go back and do this solution colloids of suspension lab. And we'll come back in here, and as you come back in, you can go ahead and start working on your problems at the bottom here. So, if you look at your lab for a minute, you guys see the day here. But go ahead and look at your lab, and I'll go through it real quickly with you. Before we go back, we want to make sure we get the pre-lab done. So what is the purpose? The purpose is to explore different ways that materials can be mixed to make new materials. Test some materials to determine what kind of mixtures they are. Determine what kinds of mixtures are manufactured for commercial and particular situations. In this activity, you will mix together water and several different materials to produce different kinds of mixtures. In some cases, the materials you are mixing are pure substances. The pure substances contain only one type of particle throughout. For instance, sugar is a pure substance. A mixture contains at least two pure substances. You may think water as a pure substance. However, most water found in nature has been different materials dissolved in it. It is, in fact, a mixture. Mostly all materials you find in nature, as well as man-made materials, are mixtures or solutions, or one or more pure substances. You will make solution colloidal suspensions. You will experience firsthand the Tyndall effect. The solutions are homogeneous, while colloids and suspensions are heterogeneous. Remember that both colloids and suspensions will give the Tyndall effect. What is the Tyndall effect? Light scattering. Yep. And number two, what liquids would show the Tyndall effect?
Colloids and suspensions.
Yes. If a liquid of mixture is let to sit and nothing settles out of the liquid, but when a light shines through it, you can only see where it enters the liquid and where it leaves, but not the path through which the liquid, what type of liquid is it?
Solution.
Good. If a liquid of a mixture is let to sit and particles settle out of the liquid, when a light is shined through, you can see the path that the light goes through the liquid. What type of liquid is it?
Suspension.
Mm-hmm. Is it easier to separate milk from coffee or milk from a bowl of cereal?
Sure.
Yep. Okay, so what you're going to do is when we go back in the back there, each of you are going to obtain 5 test tubes. You're going to fill each test tube about 1/2 to 3/4 full of water. Use the distilled water so you don't get a colloid solution already. Okay. Your first one you're going to just put none in, so you're going to fill them all about the same height. The second one you're going to put a pinch of salt in. The third one you're going to put 10 drops of milk. And since I forgot the milk, we're going to use my protein drink that I brought. So we're going to do 10 drops of the protein drink. And then in another one you're going to put 10 drops of oil. And another one about just a pinch of soil. Just put a big pinch of soil in it. It says 1/8 teaspoon, but I didn't bring a teaspoon. And then I want you to take observations. Don't stir it, don't do anything, just look at it, see what happens. Then put your finger over the top, because none of this is bad stuff for you, right? Put your finger over and shake it. Okay, now flip over the page. You'll notice on the back page there's a data table, so you're doing your observations here before you shook it. Then once you shook it, that's your observations after you mix. Then you're going to use the light to shine through to see if you can see a Tyndall effect. Then you're going to tell me, is it homogeneous or heterogeneous? Which ones were what? So by our reading that we just did, the only thing that's homogeneous is the solution. Some colloids can be considered homogeneous too. So it depends on what end of the colloid spectrum you are. And then suspensions, of course, would be heterogeneous. Then you're going to tell me what you think it is, a solution, suspension, or a colloid. Then you'll use a test tube brush and cleaner dish soap to clean out your test tubes. Please don't put solids on the sink. If they're solids, try to just put them in the garbage. It's like put water in the garbage and it'll evaporate. Okay? Then on the back side there, the post-lab questions, you're going to, by what's been said, explain what you think it is. If you can't narrow it down to more than to one, then tell me what two you're going between and what would be your reason. Okay? And then on the very back, there's some other questions that you need to answer. Any questions about what needs to be done? Okay, time is yours in the lab. Since we are using test tubes, we're using glass, you do need to wear glasses back there. Put the goggles on, you need to wear the glasses. Okay?